One of the simplest types of resonators is a device called a harmonic oscillator, and that's what we see here. It only consists of two things. It has a spring and a mass. The mass is the cube at the bottom, and it's attached to the spring, which is attached to something that doesn't move. We'll attach it to a stick, as you'll see later. We assume, for the purposes of this discussion, that the spring itself has no mass. That's not true in real life, but we pretend. If we do nothing, then the spring is pulling up on the mass, and the mass is pulling down on the spring because of gravity, and they are in equilibrium. They're pulling against each other equally, so it just sits there. The spring is stretched a little bit, but it doesn't move until we move it. So what we'll do is put some potential energy into the system. We'll lift the mass up higher than its point of equilibrium, and then we let go. As soon as we let go, what's happening now is that the spring doesn't have enough tension to keep the mass up. So the mass starts dropping, and it accelerates. As it does that, it's getting closer and closer to the point of equilibrium. But when it gets there, of course, it can't just stop. It has some momentum, so it wants to keep going. So it does. It keeps going past the point of equilibrium, down too low. And as that happens, the spring is getting stretched more and more. So it's pulling back on the mass now, so the mass slows down until the point where it stops, bottoms out, and then starts moving back upwards. Again, past the point of equilibrium, but again it has momentum. So it travels upwards too much, gets up to almost where we started, and the whole thing starts again. So we get into this cycle of it bobbing up and down and up and down. And this isn't a surprise. You've seen this in children's toys. This is not new information I'm giving you. The rate at which this thing bobs up and down is determined by the relationship between the spring's springiness, its compliance, and the mass, how heavy it is. If we make the mass bigger, if we make it heavier, then it's going to bounce up and down fewer times per second, fewer times per minute. So the frequency will be lower. The same would be true if I made the spring less springy, if I increased its compliance. Conversely, if I wanted to make the thing bob up and down more quickly, if I wanted to increase the frequency, I'd either make the mass less, I'd make it lighter, or I would increase the springiness of the spring. I'd reduce its compliance. Let's look at this in real life. What we have here is a spring attached to a stick, and the spring is stretched a little because at the bottom of it I have a mass. In this case, it's just a pair of locking pliers. And the whole thing is sitting in equilibrium. It's sitting at its equilibrium point because I haven't done anything to it yet. The mass is pulling down on the spring, and the spring is pulling back up on the mass. And then I lift it. I add some potential energy to the system. And of course what we see is the mass, the locking pliers, start bobbing up and down. What is interesting here, or what we should look at, is the frequency at which it's bobbing up and down. And we'll come back to that later. But let me just click my fingers every time it bottoms out here. So you can see that frequency is not changing, and it's constant. That's because this thing wants to resonate at that frequency. The relationship between the springiness of the spring and the mass, for the most part, doesn't change. We'll assume that the spring keeps the same amount of springiness regardless of how much it's being stretched. You can see, however, that the mass is bobbing up and down less and less as we go on here. And that's because there's some energy in this system that's being lost. It's being converted to heat. And there are two main reasons for that. One is that as it moves up and down in the air, there's air friction that's pushing the air molecules out of the way, and that's causing some heat as it goes up and down in the air, and therefore some of the energy in this system, it wants to keep ringing, but it's losing energy to heat, to air friction. The other is that it's losing energy inside the spring itself. There are what are called losses in the spring. What's happening here is that as the molecules inside the spring move against each other, it also generates heat, and that heat radiates out, and we lose energy as heat again inside the spring itself. This is called damping. So what we really have here is something called a damped oscillator. What's happening is that, in theory, if there were no losses to friction, this thing would bob up and down by the same amount forever. It would keep going for infinity. But of course we lose something and lose some energy over time, and therefore the bobbing gets less and less. It moves less and less over time. But what's interesting to note here, let's look at the frequency again. I'll snap my fingers every time it bottoms out. So you can see the frequency hasn't changed. It's the same frequency as it was before when it started moving. And that's because the relationship between the mass and the springiness, the compliance of the spring, hasn't changed. So the frequency won't change over time. All that will lose is amplitude, the amount by which the mass is going up and down as it moves.